I'm starting recording now. I think we have most of the folks in here. So thanks everybody for coming to our sea level rise seminar at NASA GISS. Patrick is on mission in Shanghai, so he asked me to do the secure Wi-Fi stuff today. We'll see how it goes. Today we have Surendra Adhikari from JPL with us. He is a research scientist at JPL's Earth Surface and Interior Group, and he works at the intersection of climate science and solid Earth geophysics. He is currently a member of the NASA Sea Level Change Team and Solid Earth Team, and his work has been recognized with the 2019 NASA Early Career Achievement Medal and the 2021 AGU John Warr Early Career Award. So, Surendra, can you take it away?
Yeah, great. Thank you. So I must thank Patrick for being patient with me. Yeah, I promised him to present something last spring, I guess, but anyway, we are here now. Yeah, thanks to everybody for being here. And yeah, as I said, my name is Surendra Adhikari. I work at JPL. And today's presentation is gonna be related to sea level sciences for sure, one way or the other. But I'm gonna keep it at relatively high level, and I put climate there. And as all of we know, sea level is an integral component of climate. So I hope you'll find this presentation relevant for what you do. In any case, so as my title suggests, I'm gonna talk mostly about Earth's rotation, particularly in light of ongoing climate change. And the knowledge of Earth's rotation is of foundational importance for Earth and space navigation and precise timekeeping. So it has relevance for all the NASA and partner agencies, space missions, and global GNSS, positioning and whatnot. Okay, all right. Yeah, so I thought I just give you a brief overview of our progression of knowledge on this topic, we as a humanity. So as far as my quick research suggests, it looks like it's been more than 20,000 years that humanity used to be fascinated by night sky. And the fact that, night after night, it appears to them that the entire heaven appears to turn westward, and that made them really curious. And then, that eventually led Aristotle and many philosophers back then to establish what we now call a geocentric cosmos, so in which Earth is placed in the center of the entire cosmos, and everything else, all the celestial bodies, were supposed to move around Earth. However, about the same time, some 2,500 years ago, some other philosophers, especially in India, uh, they 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 kind of used to think it must have been Earth. It not must have been. It could have been Earth that rotates itself, not necessarily the entire heaven. However, at the time, the very idea that Earth would rotate was considered to be a devastating or super crazy idea. But anyway, and fast forward another 1,000 years later, it took Copernicus and many other scientists at the time, they established what we now call the heliocentric cosmos, or not cosmos, heliocentric system, where Earth and the planets and moons in our solar system, they rotate about the sun instead of, about our planet. And yeah, around that time, or maybe a few hundred years later, all the hotshot physicists and mathematicians we now know of, they were intrigued by this problem of Earth's rotation one way or the other. And in the process, they have established the theoretical foundation for Earth's variable rotation. And however, it took another, well, it was not until 1851 did we had the evidence or kind of unambiguous evidence of Earth's rotation. And it was based on a simple pendulum experiments conducted by Foucault. And now the idea is that as the plane of the pendulum, if we keep the plane of the trajectory of the plane of the pendulum over many hours, we could see an apparent motion or apparent shift in the shift of the plane of the plane of the pendulum. And it is simply because the solid Earth underneath the pendulum is rotating. And so now, if you go to the leading museums globally, virtually in every museum, they have this Foucault pendulum, you know, being demonstrated in front of our eyes. That, as we observe how the path, the plane of the pendulum changes its direction, that is a testament, or that is a direct evidence for Earth's rotation. And it was not until the mid 18th century uh, that we realized, Earth's rotation is not fixed, but it varies in time. And the kind of bulletproof evidence for this one, this fact that the Earth's rotation varies in time, is based on the ancient uh, data books or manuscripts or tablets, put together by Babylonian, Chinese, and many other civilizations about the timing of the lunar and solar eclipses. And the idea is that, so now, we know the orbital mechanics at a very high precision. And if we assume that the Earth would have been rotating at a fixed spin rate as of today, I mean, like the present day spin rate, then we can back calculate for a given celestial event or given eclipse. We can say here must have, I mean, we can determine the trajectory of, say, the totality. And here is a nice example. I could see, again, assuming the present day Earth rotation, a particular event that happened on the 15th of April in 136 BC. There was the observation of solar eclipse, I guess, the totality, and yeah, it was being observed by Babylon. And so meaning they observed the event here, and if we compute based on this, the fixed spin rate using the today's value, then we can predict that if Earth would have been rotating at a constant rate, this event would have been observed along this, this path, this track. And visibly, because we can say that there is offset of about 45-degree longitude. So what that would mean is that the Earth would have, or it used to spin faster back in those days than today. And hence there is a big, huge offset. And based on this simple, but, really solid logic, the astronomers mostly, they have compiled, all those eclipses, and they have tried to determine what they call the clock error. I'll talk about it in a bit, but it is mostly related to Earth's rotation rate. And you can see a systematic drop in the clock error, which would mean that the length of day has been systematically increasing over time, at least in the past 3,000 years based on this data. Okay. Yeah, so now, then in the mid 19th century, uh, astronomers used to use, the telescope or whatever devices that they have developed or they have manufactured, basically to keep track of the occultation timing of stars by the moon, and that helps also determine the spin rate now. But the key or the main revolution really happened in the 1950s when we invented atomic clocks, and that made, it, every measurement it could make about the Earth's rotation or, the transient times of stars past any local meridian. So it will be highly, highly accurate, and you can deduce the Earth's rotation parameters highly precisely. And so, with the advent of atomic clocks, we can not only measure the spin rate of the planet, but we can also measure the wobble of the spin axis, meaning the spin axis is not fixed in time. It keeps on wobbling, and we can measure that with high precision. And for that, actually, there was, well, there is International Latitude Service that was founded in, I don't know, maybe 19, very, or yeah, early, or maybe somewhere around 1980. And the idea is that if we have a bunch of observing stations aligned along the same longitude, same latitude, as you could see in this map, is literally tracking 30-degree and 8 minutes north latitude across the globe. And what you can see is that if you keep on looking at the same pair of stars, we could see the apparent change in latitude, meaning you don't see the same trajectory of stars, even though we are observing from the same latitude. And it's been documented fairly well, very well, and it's called the apparent latitude shift. And this apparent shift is indeed because of the fact that the Earth has been wobbling, over time. Okay, so now we are in space geodetic era, and there are, bunch of high precision observing techniques, including very long baseline interferometry, which measures the radio signals that comes from the extragalactic sources like quasars and things like that. And there are, I mean, I assume we all know, one way or the other, global navigation satellite system, satellite laser ranging or lunar laser ranging, and DORIS, and all those, existing technologies that basically, yeah, and we can combine all these data set to produce a continuous time series of Earth's rotation parameters. And here I thought it'd be good to reflect on this achievement that we made in 1960s, I guess. And there you could see the big image. Oh, I can use my cursor. So this is a lunar retro reflector that was being planted by Apollo 11 mission. And yeah, I'm not sure if it is, but I think we can still ping this reflector and get some signal back from there. I basically is shooting laser signal there and then retrieving the two-way travel time, and it helps us also to determine the Earth's rotation parameters. Okay, so before I show you data, I thought I would just give you a quick overview of when we say we model Earth's rotation, what do we mean by it? So it's a very fundamental set of equations that we solve, which is called Euler's equation of motion, and naturally established or derived by Euler back in 17 something, almost 300 years or maybe more. But anyway, the whole idea is rooted in the fact that the angular momentum must be conserved for any rotating object. And the capital L here is the angular momentum, which is function of time, obviously. And on the right-hand side, for the sake of conservation, so it should be, you should also take into account the external torque being imposed by being imposed by moon or other celestial bodies. And but it can be, yeah, and the angular momentum can be broken down into two different sources. So angular momentum could be induced through what we call the relative angular momentum. Okay, I should take a step back. So the Earth's rotation parameters are determined by the angular velocity vector, omega here. And if we know the angular momentum change and also external torque, we can calculate the angular velocity vector, and which characterizes both the spin rate of the planet and the wobble of the planet, which we call polar motion. And it can show that the angular velocity vector, specifically polar motion and spin rate, they are not being perturbed, or they are not dependent on the external torque. The external torque by moon or other celestial objects would cause the planet to precess or nutate, but it does not cause the planet to change its rotational dynamics. So we simply set it to zero in our calculation, and it all boils down to the conservation of angular momentum within our planet. And here, as for any geodetic analysis, the reference frame is a critical, it's a foundational thing we need to know about. So the Earth's rotation data are distributed in what we call the mean mantle reference frame. So meaning by mean mantle, it's basically from the surface of the solid Earth, including the top of the crust, all the way down to core mantle boundary. So this is what we call mean mantle, and the idea is that any changes of the spin axis or spin rate that is being recorded is relative to the motion of this mean mantle frame. So by definition, the relative angular momentum of the changes that happens within the mantle is zero because that's the reference. However, the angular momentum exchange between the mantle and the outer fluid envelope, like ocean, ice, atmosphere, it is going to introduce the perturbation angular momentum, and hence, it can impact Earth's rotation. And so there could also be angular momentum exchange between the mantle and the fluid core, the outer fluid core, and that should also be taken into account. And on top of that, there could be another way how the angular momentum could be perturbed, and it is through the perturbation in inertia tensor. And so it could be also related to the distribution of mass on the surface or within the interior of the planet. We'll get to that in a little more detail, I guess, in the next slide. Or let's see. And the idea is that the Earth's rotation, the variation of Earth's rotation is super tiny. It's on the order of 10 to the, or maybe 6 to 8 order of magnitude smaller than the nominal spin rate or the spin position that we determine to begin with. We assume to begin with. And then the perturbation theory could be applied. It could say that the angular velocity, the mean angular velocity, has a constant rate of omega, and the inertia tensor can be also decomposed into, or maybe here, can be also decomposed into the perturb and initial state. So in the initial state, we can consider a triaxial Earth with the principal moment of inertia A, B, and C. But in practice, the B and C, the two equatorial moment of inertia, are very close to each other. So you can just simplify things. But yeah, I mean, for generality, I just keep those, the triaxial nature of the planet. And yeah, and by definition, we can say, because, we have sort of flexibility to choose the reference frame. I can choose that to begin with the initial state of the relative angular momentum, meaning the initial condition is that there is no angular momentum exchange between the mantle and outer fluid core, and also the atmosphere and ocean. And then we can perturb, think of the perturb system where you have the initial condition or the initial state, and it's just pretty perturbation. And this tiny perturbation, literally characterizes what I'll be saying, LOD, length of day change, and also polar motion. And here also you can see this initial state for the inertia tensor, and this is the perturbation term that we try to model and predict the associated Earth rotation parameters. And similarly here, we can also express the perturbation in relative angular momentum. And so what is important from geophysical point of view is that the fact that the Earth's rotation data is a three-dimensional vector. So the first two-dimension characterizes the position of the spin axis, and the third dimension characterizes the spin rate. However, it's a net sum. Whatever observation or the perturbation in the Earth's rotation vector we observe is an effect of millions of things. There's your physical interaction or mass transport or momentum transport within the Earth layers. The net effect of all or everything that happens on our dynamic planet is only reflected in the form of that three-dimensional vector. And it is really even though the physically it's not a complicated model you need to have. It's just you need to conserve angular momentum, but getting the precise or but explaining the underlying causes for this observed Earth rotation parameters is extremely challenging, simply because we live on a highly dynamic planet, as it's been described or depicted in this schematic. And I don't know what I mean to say here, but the whole idea is, I'm sorry, yeah. Okay, so essentially we want to solve for MIs. MIs are the perturbation to the angular velocity vector that characterize the polar motion and spin rate. And you can do, this relatively straightforward math, mostly analytic. And in a complex notation, you could write the Euler's equation that you see in here in this form. So there are a couple of things I like to make here. The M in bold is a complex notation for polar motion, and it has two components, the X and Y components naturally. I'll show visually with data in the next slide, I guess. And the imaginary part has, I mean, Y component is assigned imaginary part, but it's just up to how we want to define it, define the complex variable. And you might have heard about something called Chandler wobble, which is a free wobble, but it's being excited by, all this chaotic processes that happens in atmosphere and ocean. So this appears in down here. And everything that you see on the right side, these are what we call the excitation function. And the idea is that this excitation function can have direct connection to geophysical processes. And so what we do in general is that, so given a particular phenomenon, say the glacial isostatic assessment, then you can quantify the induced change in inertia tensor, and that could be connected to the in a fairly straightforward way, I guess it's written here, to the excitation function, and this would be the input to the model that could simply gives you the output, which would be polar motion in this case. And this equation is for the spin rate. And the key point, another key point to remember here is that these two equations are decoupled, meaning we can tackle the problem of spin rate or length of day change independently of the perturbation in polar motion. And in reality, there is some coupling, but the coupling is of many order smaller. So it's so easy to decouple and still get highly accurate predictions or results. An excitation function, you see a bunch of numbers here. These numbers reflect, I just wanted to make those equations bite size. And these numbers reflect so many things about the physical properties of Earth, such as mantle and elasticity and many others. I don't remember by heart. And yeah, you can see the excitation function for the polar motion, and this is for the length of day change, and you could see, yeah, C and A are again the polar moment of inertia, principal moment of inertias, and this is for the principal axial principal moment of inertia for the core. And so basically we take into account for the propagation or the transfer of, or yeah, the coupling of a core and mantle as well, but everything is folded into those numbers. And if you're interested in diving deeper, along any respect of these geophysical processes, I'd be more than happy to chat afterwards. So now, as I said here, we have two nicely decoupled equations, and so I'm gonna just have a look at my time. Okay, I'm gonna speed up a little bit now. So I'm gonna spend maybe first 10, 15 minutes on polar motion and another 10 minutes on length of day change. So polar motion, again, as I said, is the motion of the spin axis itself. And here's a nice visual, thanks to NASA Goddard Space Scientific Visualization Studio. And so if you imagine yourself flying out in the space, and if you look at the planet, and obviously it's a highly exaggerated animation, but what you really see here is the kind of the pixel of polar motion. And this is the actual data we get, by combining, using a various method to combine all the data, all the measuring technique that I tried to introduce briefly in the first 10 minutes of my presentation. And you can see, this is the millisecond of arc. So it's a small number, and which is the unit of distance in this case, right? As a function of time and for X and Y components of the polar motion. And if you do a simple spectral decomposition, and you can see that a couple of peaks really stand out. And these are fairly well understood phenomenon. And the first one is called Chandler wobble. that has a periodicity of about 433 days, and it's a free wobble, meaning it's not been excited, or it's been excited by the dynamics, mostly by the dynamics of the atmospheric and ocean circulation. Uh, but if there is no ocean, no atmosphere, it does not have to stay there. And the other one is the annual wobble. It also has a significant amplitude in the polar motion data, and it is naturally connected to the seasonal mass turnover and the fact that we have the asymmetry in land mass distribution, snow accumulation, precipitation, and all those things. However, what we're interested in is to understand the underlying geophysical connection to the polar motion data at you know frequencies larger than, or at periods longer than this channel wobble period. And the data looks like this. This is heavily smooth data after filtering out all high frequency signals, including channel wobble. And here, just imagine yourself looking down to the North Pole. And if this is the position of the pole in 1980, and this is the trajectory of the pole, and we are here literally 2024 or 23. And a couple of things I like to make here, and just pay attention to the scale here. So this is 3 meters. So which means that the spin axis has traversed by about 10 meters or something since 1900. So along the direction, literally pointing towards you guys, New York, actually. So this is the general drift direction, if I may, of the pole, uh, at least in the past 120 years. And this what I like to call the secular polar motion. And on top of this general secular polar motion, there is a variability along the way, which I'll call interannual variability, which, it had the periodicity that could be, in some cases, multi-decades or something. But anyway, in general, there are two things, or two features, which is apparent, I guess, the secular trend and some variability about the trends. So I like to talk about, so now we want to know what is causing the secular trend of the polar motion. And one natural process to think about is what we call glacial isostatic adjustment. And very quickly, this is the attempt, the glacial isostatic adjustment is the attempt of solid Earth to compensate for the lost ice mass that used to be there in mostly North Hemisphere, or North America, a Laurentide ice sheet. So if there's no more ice sheet, then the mantle material tries to compensate by flowing towards this underneath the pre-existed ice complex, or Laurentide ice sheet. You can think of that. And if that is the case, then in response to this mass migration in the mantle, which is ongoing still as we speak, it induces the change in inertia tensor, and hence the pole had the tendency to move towards this, mass loss hotspot, if you may. Meaning, they think of this as a Laurentine ice sheet, and this is the north, or the spin axis, this is the North Pole. And when the ice sheet was here, the pole was here, and there is no more ice, the pole is heading that way. So literally, so this is the location of where the Laurentine ice sheet used to be. And it's natural to presume that it must have been glacial isostatic adjustment that causes the secular polar motion. And in fact, some geophysicists use this secular polar motion as a face value for the glacial isostatic adjustment processes, and use it to constrain GIA model, in particular the mantle viscosity in the deeper part of the lower mantle, like D double prime and things like that. And however, depending upon the choice of your Earth's structure and rheology, it could end up getting various prediction of the glacial isostatic adjustment induced secular polar motion. And I'm just throwing a couple of those just to make a case that there is no consistency in how the glacial isostatic adjustment model treats the polar motion. And some models predict it fairly close to what has been observed, while others are way far out. And that's an indication that the polar motion glacial isostatic adjustment is not the only cause of the secular polar motion. And then there is an entire other community of geophysicists and geologists who really are interested in a geological time scale where the mantle flow is behaves like a fluid, like it really convects, right? Or the mantle convection. And so in the process of mantle convection, uh, in a very nutshell, what happens is that the whole mantle material uh, causes all mantle convection causes the mantle to rotate such that it promotes upwelling of mantle material in the equator and downwellings, to the poles, and such that so that it aligns with the general uh, magnetic field, the outer core derived magnetic field, and also it complies with the climatology, basically, where the equator should be and where, all those tropics of Cancer or Capricorn and all those uh, hit the sail, right? I mean, on this large scale climate pattern. And but anyway, so the point I'm trying to make here is that the researchers who study true polar wonder, they consider this polar motion data that we observe, which is 10 centimeter per year, roughly speaking, as a face value, so they can use this data to constrain their model. So now you can see already a contradiction. Right? The glacial isostatic assessment community is also saying polar motion is because of what happens in during these GIA processes, while the mantle convection folks also use this as a value that they could attribute, or they could attribute to mantle convection processes. And here is just a compilation. This is mostly the work by Bernhard Steinberger, one of my colleagues, who is an expert in mantle dynamics and mantle convection. And so well, we basically did the compilation of the existing mantle convection model, and just throw the four-model prediction of how it looks like for if we predict the present day polar motion, or TPW. And in general, as you can see, the direction, if you go back, of the observation is very well aligned with the general direction of mantle convection model prediction of true polar wonder. But the amplitude is a little small, but again, so this is another, in principle, cause of polar motion. Okay, and then there's also a thing that all of us are interested in, which is climate. And we know that climate has been really contributing significantly in terms of redistributing mass on the surface of the planet, mostly through the melting of ice caps, ice sheets, glaciers, and raising global sea level. And this is a really nice paper by one of my colleagues, Thomas Frederickson, basically trying to close the sea level budget. And you can see, as a function of time, the global mean sea level has kind of been rising sort of steadily, but it has been really ramping up in the space era. And now the point here is that Walter Munk had a really great paper published, well, almost 2 decades ago, and he was making a case that if the Earth's rotation is, well, the climate induced surface mass distribution like sea level change and ice melting, it is true, right? I mean, it is a fact that we have been, I mean, it is a fact, and it should also induce, in principle, the polar motion. And if the polar motion data is attributed to glacial isostatic adjustment or mantle convection, then there should also be some share of climate to the polar motion data. And hence there is an inconsistency in the 20th century sea level uh, reconstruction and the polar motion data. And I've tried to highlight so I don't misquote what he meant to say. And so Walter Monk says that there are three possible resolutions for what he calls the sea level enigma, and one would be a substantial reduction of the 20th century sea level change from 1.5 to 2 millimeter per year, and or there could be a substantial increase in the estimates of ocean heat storage, meaning sea level could rise by even 2 or 3 millimeter per year, but if it all happens because of ocean expansion, it does not really induce the inertia perturbation, and hence the polar motion. And so finally, or there must be a substantial change in the interpretation of astrometric records. So by astrometric, he means to imply the polar motion and length of the data. And this is so given our understanding, I mean, there is a tremendous understanding of modeling climate of the past, or by past I mean at least the 20th century, or since the Little Ice Age. or the inception of industrial era, whatever you prefer. But anyway, so there is, we tend to think the 20th century sea level uh, reconstruction or our knowledge is fairly accurate. And we also tend to think that it's not only the stereodynamic changes, but it is also this barostatic or the mass related changes, which means that there must have been associated uh, or some significant contribution to secular promotion. And this led us to kind of try and highlight the last option that he put together, which is the need for substantial change in the interpretation of promotion data. And that's what we tried to do in a paper that we published a few years back, and where we tried to do a really robust Bayesian inferences of the glacial isostatic adjustment induced polar motion. And here the observation and bunch of dots would say that you can literally choose any uh, reasonable Earth structure and viscosity structure and get a polar motion as twice as much. But obviously, it should also comply with other constraining data sets like the deglaciation sequence and paleo relative sea level data. But anyway, so our prediction was that it's most likely the glacial isostatic adjustment contribution is somewhere around here instead of here. And then we also did the climate-induced or calculation of the polar motion, which is literally based on the lateral transport of mass between land and ocean. And then we found that if we there are a handful of the matter convection model that could help us resolve this enigma, meaning we could still explain the polar motion data by putting all three major players together, which is glacial isostatic adjustment on the left and mantle convection on the right, and also the climate. So again, it's not a settled thing, but yeah, we think there is a way to reconcile all these various processes within this or from the Earth's rotation point of view as well. And there is interannual polar motion as well. I'm really falling behind. And again, so the key point I like to I said it again, but there are wiggles along the way, and the periodicity of the wiggles could be anything between many years to as long as 30 years, and some people call 30-year periodicity of polar motion is also like a Chandler wobble, a free wobble, and they even call it a Markowitz wobble. But from geophysical point of view, we don't have to necessarily label different signal at different periodicity. Anyway, so for us, it's all wiggles along the way or about the secular trend. And the amplitude could be fairly large. It could be about like a meter swing in the drift direction. And so because I need to speed up, and we know this is Grace is let me go back, sorry. So I'm gonna mostly focus on the last piece of wiggle since literally the beginning of this millennia, uh, and this time frame also coincides with the period of Grace and Grace follow-on data, and we know how amazing Grace and Grace missions, follow-on missions are in terms of capturing the global scale mass transfer. It's just a Grace data showing making the same point that Grace is great. And so if we know, for example, how much mass is being added or lost from a particular part of the planet, we can forward model the associated ocean mass redistribution. So the mass is conserved on a global scale, but we also, and the spatial pattern reflects the fact that the ocean mass is being redistributed on a viscoelastically compressible planet, on a self-gravitating planet, on a rotating planet, which is Earth. And you can see, yeah, that's all I say here. During the this rather outdated chart that we published back in 2016. So what you see here is literally the x component and y component of polar motion. I call it chi1, chi2 as a function of time. And the red is the observation based on the polar motion data. And the black is the model prediction mostly based on the GRIS data. So the point is, GRIS data is great. GRIS data is great again, but in the sense that it also complies with this, this relatively recent wiggle that we see in the polar motion data since 2000, if you recall the animation I showed. And yeah, so now if you look at the Y component, there is a significant interannual signal you could see here, or at least I see it, which is just follow this shaded shine color background. And the Y motion or the Y component of pole was going uphill and it started coming downhill. So because our prediction not only matched the trend, it also matched, if you follow the red and black line, it also kind of tracks this general interannual variability. And because the reconstruction is a combination of all the contributors as measured by GRIS, we can disentangle, what is the source of this interannual signal? And then we find that this interannual, the source of the interannual signal is essentially coming from the terrestrial water storage or hydrology, I call it. If you just follow the black line, sorry, blue line, so this is really going up and coming down. And this dominates the interannual signal that we observe in this GRIS observing period. And the same thing, just really trying to make a using some existing animation that we prepared. So what happened if you really look at the GRIS data? So between the 2005 and 2015, when the pole motion was going up, this is a pattern of mass change. And afterwards, the pattern looks like this. There are a couple of things you might immediately see. So one is the intensity of the signal, the darker color here, which means the faster polar motion. And there's also the flip in the color. So you can see, for example, Australia, it used to be red, meaning gaining mass, a lot of precipitation, I guess. And now it was experiencing drought in the after years. So the point that we wanted to get across in the paper that we published back then is that so the fact that on an annual or decadal time scale, there is a large scale, the continental scale mass redistribution on the surface of the planet. And it is being fairly well known as the global wet dry spell. And we think that's the main driver of this interannual polar motion. And then sorry, I am really falling behind, but yeah. And then we did, I was contacted by a PhD student, Mustafa Shavendi, back in 2022, and he wanted to do some high impact research on Earth rotation. And he comes with a machine learning, computer science background, not much knowledge in geophysics, geodesy. But anyway, so what we did together is that we thought, for the grace period, or if you just go back to maybe or during the space era, let me say this way, we have some handle on the Earth's surface mass redistribution, but we don't know much about what might have happened in the past. Although we not all of us don't necessarily agree on that, but so he deployed machine learning real quick, trying to capture the mental processes, glacial isostatic and mental convection processes, the seismic processes, the interaction between core and mantle, and the climatological processes, which is ice water mass exchange mostly, and also the land water mass exchange. And then we try to minimize the misfit between the underlying physics and what the model would learn, and also the data polar motion and any geophysical constant that you could find. And what we found is that if you have, and this is our training period, sorry, I'm really sketchy here, but this is our training period, and we wanted to reconstruct going back in time because we have a solid data, which is the red line, I guess. And if we just train the model with a conventional machine learning algorithm and you just let it go without putting any physics in the neural network, it just gives you random wiggles, right? It doesn't make any sense, the green line. And then we systematically can put different processes, and then we can show that if we put all processes together, we could reconstruct the observation fairly well, which is the black line. And this literally shows the relative contribution of different processes. And yeah, I don't have time, sorry. The key takeaways, and then again, the whole idea of doing this is that we can disentangle the contribution throughout the 20th century. And what we find is that the long-term geophysical processes such as mantle convection and glacial isostatic adjustment, this color is really driving the secular component. And the non-secular variability is mostly related to interhemispheric or intercontinental, it should be, water storage change, including ice and water mass distribution and sea level, which you see in green. And what we also found is that there is some non-negligible in an annual pattern associated with the core dynamics. And if you really observe the phase of the purple line, I'm just pointing on one of the main signals here, and the green line, you see the anti-correlation, right? When it has a positive amplitude, it has a negative, and so on. And which would mean that, which would indicate that there could have been an interactions between the what happens in the outer fluid envelope and inner fluid core, or outer fluid core, and the climatological processes in a nutshell. This is just a degree to really long wavelength interconnection. And we have opportunity to explore along that line, literally trying to understand if there is some connection between climate system and the core dynamics. And the our main goal and the most exciting thing for us is that because we can disentangle contributing processes, we can use corresponding processes to constrain the corresponding or the respective geophysical and climatological model. Let me know if I need to stop. I have few slides. I have less than 10 minutes either way, but I'm done with the polar motion part. Sorry. What do you guys think?
I think you should carry on.
Okay, yeah, real quick. So this is now the second part, the Earth's rotation. And this is a nice animation. It shows the fact that the Earth's rotation is not constant. So if you imagine yourself, maybe one of the guys here, and try to keep track of your angular position precisely after 24 hours, you end up not making a full circle simply because Earth is not rotating at a constant rate. And this is the basis of, when we say think like leap second or, leap year, or maybe not leap year, but leap second, is literally related to the fact that we want to comply with atomic clock, but also we want to comply with the general spin rate of the planet for obvious reason, because we don't want to have sunrise, at 3 a.m. or something. I'm just making things up, but yeah, you see the point. So this is a really long time scale, 2,500 years, the same clock error data from the eclipses that I showed before. And if you just do a first derivative of these lines, you get the length of day change. And the key point here is that this is the black line is the inferred length of day change from eclipse data. And you can see a underlying trend, the green line, which is about 1.7 millisecond per century systematic lengthening of day over the past 2,500 years. And so the tidal friction alone, which is the angular momentum exchange between the moon and the earth, and all the tidal bulges that we see in the ocean, and we know, there's an elasticity of a solid earth. And taking all this together, it could quantify the tidal friction, could contribute up to here, but there is a systematic gap between the two. And then people have been thinking it could be because of glacial isostatic adjustment or core mantle coupling or climate-related processes. And we really wanted to explore the climate aspect for a couple of reasons. Even though the climate contribution for the past is shown to be negligible or small, so we still look at climate for a couple of reasons. Because we might also, we thought we can extract the glacial isostatic adjustment signal from some other data sets, which is satellite laser ranging data of Earth's obliteness. And the second reason was that because the climate is really ramping up, so even though its contribution to the past secular length of day change is not much, it may be a key player moving forward because it's been contributing significantly already. I skip this. And just okay, so this is the Earth rotation data in the past 120 years. Sorry, length of day data. And this is the climate contribution that we can forward model. And you can see that Earth rotation, length of day data is mostly overwhelmingly dominated by the core mantle processes. And it is hopeless to extract any meaningful uh, climate signal out of the length of day data. And So even though we forward model, we cannot even validate if our forward model is consistent with the observed length of the data. But fortunately, we also have a complementary data, what I like to call, which is called J2 data as a function of time. It goes back to 1976, mostly from satellite laser ranging data. And so J2 data and the length of the data, they have some common processes that cause both the data set, that contribute to both data set, but the obsolete data is much straightforward, and it's just a subset of the processes that goes into determining the length of the data. And hence, the point that we're trying to explore here is that let's just look at the J2 data. We know there are two primary components, is the ongoing climate change and also the glacial isostatic adjustment. And if you can forward model climate change, it's literally the same data here, but different scale, then you can see this higher order curvature in the observed data is pretty much gone. And what is left over is what we think is the glacial isostatic adjustment signal. And now going back to this really long time scale secular trend budget, we had the tidal friction, pretty big tower, and the observation is here. Uh, and sorry, I'm just looking at it. And so, okay, and then because there is a gap between observation and tidal friction, we wanted to explain that. And this is our, relatively speaking, independent observation of glacial isostatic adjustment data based on the knowledge of climate of the past 30, 40 years, and also the knowledge of the Earth's oblateness based on the Z2 data. And if you sum the two, there's purple and this color, and we end up getting a fairly similar uh, tall tower as the observed data. And we think that the GIA alone can explain the data model misfit on a really secular time scale for length of the data. And which would also mean that the core flow, as it is extremely complicated to constrain, maybe it does not contribute so much to the equation that I tried to put here. So maybe this we should also, proceed again, just maybe. And the climate, as I said, was not really contributing in the past, but however, it is really going to contribute significantly in the future. And this is just a forward model under RCP 8.5 and 2.6 scenarios. And you can see that, under high emission scenarios, it could be that the linear trend in the length of day change induced by future climate change or future scenarios, high emission scenarios, maybe as large as the contribution from the tidal friction. So that's a pretty significant statement to make, I guess. But sorry, I'm really tumbling because of time limitation. But this is my final summary, which is basically mostly giving a perspective from climate point of view. So climate-driven mass distribution has significantly impacted Earth's rotation, at least in three different ways. The first one is by altering the long-term drift direction of the spin axis, which is largely driven by ice sheet meltings, in particular Greenland ice sheet. And the second is by inducing interannual variability in the spin axis position, mostly driven by intercontinental terrestrial water storage changes, mass transport. And finally, it has also contributed, climate has also contributed to Earth's rotation by slowing down the spin rate and increasing the length of day. And possibly its impact could surpass the lunar contribution by the end of the century. Final slide. So I have learned a lot from all of these guys, and this is a teamwork, and I really appreciate their contribution, and I thank them for everything that they have done to enhance my knowledge on the topic. And thank you all of you guys for being patient and being so attentive. Yeah, let me know if you have any question. Let me stop sharing.
Thank you very much. That was super nice. I'm gonna stop recording.